For as long as electric vehicles have existed as a serious product category, engineers have lived with one unspoken rule. A motor could be blisteringly fast, or it could be efficient and cheap enough to build at scale, but never all three at once. That trade-off wasn't treated as a temporary limitation waiting to be solved. It was treated as something closer to a law of physics, the kind of boundary experienced engineers simply stopped arguing with. Tesla's newest motor appears to have quietly broken that rule, and the people who've taken one apart to study it are not describing the moment with excitement. They're describing it with unease. The numbers alone are enough to raise eyebrows. A luxury sedan built around this motor can reach 60 miles per hour in under 2 seconds, a figure that used to belong exclusively to million-dollar hypercars. The rotor inside spins at speeds normally reserved for industrial turbines, not passenger vehicles. And somehow, it costs a fraction of what rival automakers spend chasing far less impressive results. When independent teardown specialists opened one up to see how it was done, what unsettled them wasn't the top speed. It was what they found wrapped around the spinning core. To understand how Tesla got here, it helps to remember how differently this story was expected to end. A little more than a decade ago, most serious industry analysts assumed Tesla would be a footnote, an ambitious startup that helped kick off the electric vehicle era before being quietly overtaken by manufacturers with the manufacturing scale, supplier networks, and engineering depth to actually finish the job. Compared to century-old giants with global factories and decades of institutional knowledge, Tesla looked exactly like what it was: small, unproven, and fragile in all the usual startup ways. For a while, that prediction seemed to be tracking. Competing electric vehicles kept improving. Battery technology matured faster than expected. Analysts began writing that Tesla's early lead was shrinking, and that the rest of the industry was finally catching up. Then Tesla introduced a new drive unit, not a flashier body style or a bigger battery, but a motor, and the ground shifted under the entire conversation. When engineers cut one open, the detail that stopped them wasn't the horsepower figure on a spec sheet. It was a layer of material wound tightly around the rotor, doing something conventional wisdom said shouldn't be achievable at this price point. The timing of this breakthrough matters almost as much as the engineering itself. It arrived while Tesla badly needed a win. The Cybertruck, once marketed as the company's boldest statement about the future of personal transportation, had become something closer to a liability. Sales landed well below expectations. A notable share of early deliveries reportedly went to companies with ties to Tesla's own leadership, and recalls piled up in a market suddenly full of credible electric alternatives. For a company whose entire brand rests on the idea that whatever it touches redefines its category, a stumble that visible mattered. The response couldn't be a paint option or a marketing push. It needed to be something that changed what was physically possible, not just what looked exciting in a showroom. So what exactly is inside this motor that has engineers so rattled? At the center of every electric motor sits a rotor, spinning at extreme speed and generating centrifugal force that fights to tear the component apart from the inside. Conventional rotors handle only so much of that stress before they warp, shed material, or overheat past the point of usefulness. Tesla's solution was to wrap the rotor in carbon fiber, a material aerospace engineers and motorsport teams have trusted for decades because it offers enormous structural strength without adding meaningful weight. Think of it as a containment sleeve, holding the spinning core together under forces that would destroy a standard design. The result is a motor that spins past 20,000 revolutions per minute, a number almost never associated with a passenger car. Speeds like that typically belong to industrial turbines and lab centrifuges, not a family sedan parked in a suburban garage. But raw rotational speed isn't the real story here. What actually matters is how stable the rotor remains while spinning that fast. The carbon wrap keeps vibration under tight control and holds the rotor in precise balance at velocities where even a tiny imbalance would normally be catastrophic. That stability translates directly into magnetic efficiency. More of the electricity pulled from the battery turns into forward motion instead of bleeding away as heat and wasted noise. That single efficiency gain cascades outward in ways that are hard to overstate. Enormous torque, blistering acceleration, strong range on long drives, and critically, a motor that runs cooler than its rivals under identical conditions, which matters more than it sounds like it should. Cooling systems are heavy, expensive, and take up space that could otherwise carry battery cells or cargo. Most competing automakers are still bolting on pumps, radiators, and coolant lines just to keep their motors from overheating during hard use. Tesla appears to have engineered a large chunk of that problem away before the vehicle ever reached production. The clearest public demonstration of what all this enables is the Plaid variant of the Model S. 3 of these motors combined, producing over 1,000 horsepower, launching from 0 to 60 in under 2 seconds, all while still functioning as a comfortable family sedan capable of several hundred miles on a single charge. Which raises the obvious question every competing engineer is reportedly losing sleep over. If this design is faster, cooler, cheaper, and more efficient at the same time, why hasn't anyone else simply built one? They have access to the same physics, the same textbooks, and in some cases far deeper pockets. The uncomfortable answer has almost nothing to do with the idea itself and everything to do with manufacturing it at scale. Wrapping a rotor in carbon fiber sounds simple in theory and becomes a nightmare in practice once you try to do it thousands of times a week without an unacceptable failure rate. The material has to be wound around the rotor under exact, unwavering tension, then cured under carefully controlled heat and pressure. Wind it too loosely, and the rotor flexes and fails under load. Wind it too tightly, and the fibers crack during curing. Miss the timing or temperature window during the cure, and the entire unit becomes scrap. Every finished rotor then needs to be balanced to tolerances most factories have never had to hit, because an imbalance invisible at highway speeds becomes a violent, self-destructive vibration at 20,000 revolutions per minute. A competitor can't simply photograph the finished part and copy it. They'd have to rebuild the entire manufacturing process from scratch, absorbing every failed batch and wasted rotor along the way, a process Tesla has already spent years and enormous sums paying for. The difficulty doesn't stop at the rotor itself, either. A motor like this can't just be dropped into an existing assembly line. Tooling has to be redesigned around it. Quality control processes have to be rebuilt from the ground up. Technicians need retraining on materials and tolerances they've never encountered. Suppliers have to hit specifications many have never been asked to meet. None of these problems are impossible individually, but a competitor has to solve all of them simultaneously while still running a functioning business, which is a very different challenge than solving one clever engineering puzzle in isolation. This is why outside observers keep underestimating how durable Tesla's advantage actually is. The theoretical concept of a carbon-wrapped rotor isn't new. Plenty of engineers across the industry understood it well before Tesla began shipping one at volume. The hard part was never the idea. It was turning that idea into a component that rolls off a production line thousands of times a week at a price that doesn't sink the business, with a defect rate low enough to survive contact with reality. That's not something you can extract from a technical paper or a competitor's press release. It's years of accumulated, unglamorous process knowledge. And that kind of knowledge doesn't transfer quickly, no matter how much capital you throw at it. Tesla has reportedly stated that its next-generation drive units, built around this same carbon-sleeved architecture, are being engineered specifically for manufacturability, the ability to produce them quickly, consistently, and at massive scale without draining the company's margins. The target cost for a complete drive unit, including motor, power electronics, and gearbox, is set to sit around $1,000, while some competitors reportedly spend 3 to 5 times that amount to reach comparable performance. Multiply that gap across hundreds of thousands of vehicles a year, and the resulting margin difference can fund entirely new product lines while rivals are still fighting to break even on the electric vehicles they're currently shipping. Tesla is also reportedly working to reduce its dependence on rare earth materials and expensive semiconductor components, steadily removing the supply chain choke points that continue to squeeze everyone else. It's worth remembering that building an impressive prototype is one thing. Plenty of companies can unveil something dramatic, generate headlines, and attract investment for a few weeks. Building millions of vehicles consistently at prices real buyers can afford, while still turning a profit, is an entirely different discipline, and it's where most competitors have struggled. Ford's electric vehicles have earned real praise, but have also reportedly generated steep losses for the company's EV division. Lucid has produced genuinely impressive luxury vehicles, while burning through capital quickly. Rivian has struggled to bring production costs under control despite enormous investor enthusiasm. General Motors and Volkswagen have both faced manufacturing delays and software issues that have shaken investor confidence in their electric lineups. Catching up to Tesla, in practice, has mostly looked like losing money slightly more slowly than the competitor standing next to you. Among global rivals, China's BYD stands out as the one company genuinely competing at volume. But its strategy is built primarily around affordability and enormous output at lower price points, which is a different challenge than what Tesla is attempting. Tesla appears to be chasing something harder, vehicles that are simultaneously fast, efficient, technologically advanced, and cheaper to produce than anything else on the market. Being affordable is achievable. Being affordable, while also being genuinely aspirational, fast, and efficient all at once, is a combination almost no other company can currently claim to deliver at scale. Here's where most people's mental picture of Tesla starts to break down. It's easy to think of Tesla as a car company that happens to make good motors. That assumption might turn out to be one of the most expensive misreadings in the history of the auto industry. Tesla has spent years quietly stitching together several distinct industries into one interconnected system, and the motor sits near the center of it, feeding everything built around it. Start with data. Every Tesla on the road is constantly gathering information about driving conditions, road behavior, weather responses, and the countless rare situations that only reveal themselves after millions of hours behind the wheel. Autonomous systems improve the same way a human driver improves, through accumulated real-world experience. And Tesla has amassed more of that experience than almost anyone else on the planet. That lead compounds on its own. More vehicles on the road generate more data trains better systems, and better systems attract more buyers who generate even more data. A late-arriving competitor can't simply buy that history. They'd need years of vehicles already on the road just to start closing the gap. A cheaper, harder-to-copy motor means more Tesla sold, which means more rolling data collectors, feeding the company's broader intelligence efforts. Then there's the battery. Tesla invested heavily in developing its own cell technology because the battery is typically the single most expensive part of any electric vehicle. Most competitors still buy cells from outside suppliers and pay a markup for the privilege. Building your own cells means designing the battery and the vehicle around each other from day one, instead of waiting on someone else's production schedule. Tesla also designs much of its own software, chips, and power electronics in-house, a decision that paid off dramatically during the global semiconductor shortage, when Tesla reportedly rewrote its software to work with whatever chips it could actually source, while other automakers were forced to halt production lines entirely. The charging network tells a similar story. For years, it was dismissed as a nice-to-have convenience feature. It's since become one of Tesla's most durable advantages, mostly because it simply works. It's fast, reliable, and doesn't require fighting with broken screens or confusing payment systems, problems that plagued many competing charging networks. Eventually, even direct competitors gave in. Both Ford and General Motors adopted Tesla's charging standard so their own customers could access Tesla's infrastructure. That means Tesla's rivals now depend on Tesla's network to keep their own buyers happy, and Tesla earns revenue every time a competitor's vehicle plugs in. That's not ordinary competition. That's a company controlling the infrastructure its rivals are forced to rely on. Zoom out far enough, and Tesla starts to look less like a car manufacturer and more like a technology platform that happens to sell vehicles as its entry point. The company has invested heavily in custom computing infrastructure built specifically to train artificial intelligence systems on the enormous stream of driving data its vehicles collect worldwide. More vehicles on the road accelerates system development. A cheaper motor makes more vehicles economically possible. Those vehicles generate the data that trains smarter systems. The loop feeds itself, and every cycle makes the next one a little cheaper to run. A competitor entering late doesn't just start with less data. They end up paying full price for lessons Tesla already learned years earlier. Control the vehicles, and you control the data flowing from them. Control the data, and you shape the systems built on top of it. Control the systems, and you have a real claim on what transportation looks like a decade from now. That's not a small head start. It's arguably a fundamentally different game than the one most competitors think they're playing. None of this means the race is decided. Tesla has been wrong before in both directions, and its rivals aren't standing still. Battery chemistry could take an unexpected leap forward. A manufacturing breakthrough somewhere else in the world could compress this cost gap faster than anyone currently expects. But the shape of the competition has clearly shifted. For years, the question in this industry was simple: who can build the better electric car? This motor has quietly turned that question into something much harder to answer. Who can build the entire system underneath the car, the one that gets cheaper and smarter the longer it keeps running? Right now, very few companies have a convincing answer. So here's the question worth sitting with. Is this the moment the electric vehicle race effectively tips in one direction for good? Or is there still enough time and enough uncertainty in battery technology and manufacturing for a rival to close the gap within the next decade? The motor itself was never really the headline. It was a signal, a quiet warning, sitting on an engineering workbench, that the old rules everyone had agreed to play by might not apply anymore.